Hello everyone. Today I'll be talking about my final project for Columbia's Advanced Big Data Analytics class, Swift-HAR, Human Activity Recognition on iPhone 6s. Previous work on this subject has focused on the Android operating system. With the Android, researchers have created an in-device data logging and classification which is optimized for a Samsung Galaxy S2. This uses the accelerometer and the gyrometer to predict user action through fixed point arithmetic SVM. On the iOS, data is logged with an iPhone, but the processing and the training of a classifier is done in the cloud or on a laptop. There's also a proprietary platform by Atlas Wearables based out of Austin, Texas, that uses a watch or a wristband type device to record accelerometer and gyrometer data and push it through a pre-trained classifier. The goal of my project will be to bring the iOS platform up to the same level as the Android and the proprietary platform by creating an app that can record accelerometer data and do the training and the testing of a classifier directly on the iOS device. My previous work has focused on researching the current work on different platforms, the Android, iOS, and the proprietary Atlas Wearables platform, learning how to use Swift and Xcode, creating a sensor data logger app, and then using all that to create a binary classifier that is able to classify a user, whether the user is standing or walking. Now for this part of the project, I've extended the classification from 2 actions to greater than 2 actions. I've tested it using standing, walking, and bicep curls. Here's an overview of the project, or the app. The iPhone has a 3-axis accelerometer that is accessed through the CoreMotion framework, along with a user action input that determines what the user action is doing. This data gets pushed to a data processing algorithm that normalizes the data, bootstraps the samples, and splits it into a train and test set. Now bootstrapping works here because we're assuming that the actions we're classifying is repetitive and continuous. So let's say I'm walking. If I'm walking for 10 minutes in a straight line, whether I am looking at the first 1 minute or the last 30 seconds, the data in the accelerometer will look roughly the same, and I'll show that in a second. Then this data gets pushed into a feed-forward neural network to train the neural network. And then this neural network will be ready for inference. So here we can see standing data and walking data taking at 100 Hertz. You can see that with the standing data, the accelerometer values are pretty still. This is for someone that's holding the phone roughly at the same angle they would be if they were texting. And for walking, you can see that it looks like a pretty periodic signal. So if I'm to chop it up into little bits of about 1 to 2 seconds, that can be kind of representative of the population of that data. Now here I'm comparing data of someone walking to someone doing bicep curls. Here the phone is strapped to someone's forearm using a forearm armband. And you can see that both of these data look pretty periodic, but with the walking data, the values, the magnitude, and the frequency is different from the bicep curl data. We're going to try and use these differences to classify these different actions. Now here's what it looks like once it's bootstrapped. You might notice that on the x-axis, instead of having seconds, I've changed this to input nodes. And that's because we're combining the x, the y, and the z accelerometer data into one set to go into the neural network input nodes. Because the input nodes don't really care where it's from just as long as it's always consistent. So here nodes 0 to 99 is the X data, nodes 100 to 199 is the Y data, and 200 to 299 is the Z data. The neural network structure includes 300 input nodes, as you can see from the previous data, 240 hidden layer nodes, and the output layer is equivalent to however many unique actions the user has logged. So let's say I've logged standing, walking, and bicep curls. I will then have 3 output nodes. If I just log standing or walking, I'll have 2 output nodes. And if I logged standing, walking, running, and bicep curls, I'll have 4. The error threshold I'm using currently is 0.05. And this number is arrived more or less through try and error. It's a balance between accuracy and training time, because we don't want the user to be waiting around forever and not being able to use their phone for 10 minutes. With an error threshold about 0.05, the neural network trains in under 30 seconds. So now let's look at what the UI looks like for the app. On the left, you'll see the start screen that pops up. The top 6 fields up there is the accelerometer and the gyrometer data if the app was logging live. Now you can see over here, this app console displays the current status of the app and what it's doing. It's kind of like the console on a Linux machine. This text field is where the user can input the action that they're currently doing so that the neural network can be trained. Whenever a user wants to record data, they'll put, say, standing or walking over here, press record data, and it will record. Now this button, clear memory, will actually clear all the previously stored data so a user can start fresh. Let's say I click the record data button and I put this as stand, so you see the keyboard pops up here. Then once it's all trained, I can do it again with walking and bicep curls. I can train a neural network and use this guess action button so that to let the neural network guess my actions. Here's what it would look like once it starts guessing. So you can see here, I've trained it for standing, walking, and bicep curls. The neural network will identify the greatest number out of the 3 and match that to my action log. So here it says 0.99 greater than these 2, so therefore it should be a bicep curl. So let's look at a demo of what the app actually does. Here the user is going to log standing data. As you see, the phone is strapped to the forearm using a forearm armband. The user typed stand in here and pressed record. Now it's going to start logging. After about 15 seconds, the logging will be complete, and that data will be exported to a CSV file as well for analysis if the user would like. Now here we're trying to log standing data. So let's go to the walking data. Here we go. Walking data. Here we do walk, record. User's walking. Now again, about 15 seconds later, it will say complete. There we go. So let's look at bicep curl logging. Play this. Again, the user will input the action over here and press record. And as you can see, the previous 3 actions, periodic and continuous. Now the logging is complete. Let's look at the training function. Once the 3 actions that we want to look at is complete, we can now train a neural network, like so. We'll press the train neural net. We'll start training, and it'll say training complete. Now we can guess our actions. So let's say we're standing still and we want it to classify. Guess our action. It's going to do the same thing, log data for about 10 to 15 seconds. Here we go, logging is complete. And the neural network predicts that the user is standing. You can see the greatest number is in the first column. That's because we recorded standing first. Now let's look at walking data. So here the user is walking, starting to log the data. And again, about 15 seconds later, the logging is complete. And it predicts walking. So you see the greatest number is in the middle. That's because we logged walking second when we were training the data. Training the neural network, So now the third action, bicep curls. Again, guess action. The user is doing the same action as when they were trained, when the neural network was trained. So here it should be complete. And here you see that the neural network has predicted bicep curls. The greatest number is the third number, and that is the number that we were looking for. That's the third action that we logged. So to conclude, Swift-HAR includes a tri-axis accelerometer data logger, a data bootstrapper, and an expandable neural network based classifier. Now, the classification works for the three actions we've looked at, but through testing we've also noticed that the action classification decreases as more actions are added. So if there's 5 or 6 or 7 actions, the accuracy starts to decrease pretty dramatically. And the Swift-HAR also has difficulty classifying actions that have very similar acceleration magnitudes and frequencies. So let's say I'm walking, but my jog is very similar to my walk, or I'm jogging and my jogging is very similar to a slower run, then it'll have some difficulty looking at that. Or the difference between a bicep curl and a tricep curl, it does have some difficulty looking at that. Now in the future, I'd like to try some other types of neural networks or classifiers to try and minimize these problems. Perhaps adding a Fourier transform to the data processing chain will also help to mitigate some of the problems, because then we can use low pass filters or something like that as well. And also to mitigate problems with similarities in the acceleration magnitude and frequency, we could also incorporate a gyrometer, because maybe the gyrometer data will be slightly different than the acceleration data. If you'd like to look at the code that's available in these 2 locations, both of these will be updated regularly. Thanks for listening.